Great. So hello everyone, welcome to another session of your blog. I'm your host Akash Kundu. I'm a PhD student at the Institute of Theoretical and Applied Informatics for Discipline of Science. And today as a guest speaker we have Debasmita Bhoumik, and she's going to talk about the applications of machine learning techniques for quantum error correction, which is indeed a very interesting topic. And before before I give the stage to Debasmita, I want to give a small introduction about her. And she pursued her bachelor's and master's from University of Kolkata. And when she was studying her bachelor's and master's, she secured a first-class pass rank in the University of Calcutta, which is indeed a very big achievement. And at the same time, during her study in Beacon College, which is under the University of Calcutta, she was a gold medalist. And currently, she is a research fellow at the Indian Statistical Institute, Kolkata. And at the Indian Statistical Institute, she is working in the applications of machine learning in quantum computing. And apart from her research and her achievements, I would also like to add a few more words about her. That we're all aware that in the science, technology, engineering, and mathematics, we see a very few female researchers, and this number drastically get decreased when we constrain ourselves in the field of quantum. So to our guests today, Debasmita is not only a female researcher in the field of quantum, but she just became a new mother as well. So congratulations, Debasmita, and her journey, enthusiasm, and achievements are undoubtedly inspiration to all of us. So without further ado, I'd like to give my congratulations to her at the same time, and the stage is all yours. Thank you very much.
Thank you so much. Thank you for this platform where we can share our ideas and learn together. So let me first share my screen. Is this visible? Okay. So today I am going to share what I have learned during my work, which is in the application of machine learning techniques for quantum error correction. Quantum computing and machine learning are basically two big buzzwords, and what happens if we bring them together, that is our discussion. That is our discussion. But one disclaimer is this is not quantum machine learning. This is purely about classical machine learning. So we will go through a brief introduction about quantum error correcting codes. We will study decoder named minimum with perfect matching, and then we will see why this machine learning concept is brought into this. Next, we will see the basics of machine learning ideas, which is exclusively for the non-ML persons, and then we will go through which noise models we are using, followed by how to simulate the error syndrome pairs in this purely implementation level details, and finally we will check whose performance is better, the ML or non-ML. Now we all know that the advantage of quantum computers, and we also know what is a qubit and all those stuff. So I am not going into those details, but the problem is in the quantum algorithms and protocols, consider an ideal scenario, right, where the qubit is in complete isolation from its environment. But in reality, the qubit basically interacts with the environment, and as a result, it undergoes some unwanted rotations, and we term them as errors. So the solution is basically quantum error correcting codes, or QECC. So there are some popular quantum error correcting codes like short code, steam code, Laflamme code, etc. These codes suffer from a very popular problem called nearest neighbor problem. So what happens is basically to do the operation between two qubits, they have to be neighbors. But let's see this circuit. This qubit and this qubit, they are not neighbors. This qubit and this qubit, they are far away. So one qubit must be brought closer to another qubit, and that will require multiple qubit swaps, and the swap gates can be noisy itself. As a result, more and more errors can be incorporated. Hence, to avoid this particular problem, surface code was introduced in 1990. So this is basically a surface code structure. A D cross D lattice. Here we can see a 3 cross 3 distance 3 surface code, a 3 cross 3 lattice. Physical qubits, I mean where the informations are being stored, are called the physical qubits. They are on the vertices like the numbers 0, 1, 2 and up to 8. So these 9 qubits are the physical qubits. And in the plackets, the gray and white area, the plackets are also called stabilizers or measure qubits. And we can see the same image in a colored picture, that pink parts are the plackets indicate the stabilizers which can take the Z parity of the qubits. That is, if there is any phase flip errors. And the purple takes the X parity, that if there is any bit flip error. So X means there is some bit flip error. So if there is any bit flip error here, this is the qubit, then these two corner stabilizers can detect the error. And if there is some phase flip errors, that is Z errors here, then these two corner plackets can detect the phase flip error. And Y error is the combination of X and Z. Then if there is an Y error, then it will be detected by both the X and the Z stabilizers. And here we can see the circuit for the measurement qubits, like for the Z measurement and X measurement. And you can see this is a 8-step circuit with some C nodes. And if we notice that these C nodes are basically between neighbors, because suppose consider this 4, this is a qubit, right? So if there is any error, it will be caught by these two stabilizers. And this qubit is basically C noted with only its 4 neighbors, that is AX1, AX2, AZ1 and AZ2. So we will never need any swap gate, so there will be no nearest neighbor problem with this kind of structure of surface code. Now, similar to any classical error correction, quantum error correction also involves a kind of repetition. We know copy pasting is not allowed in quantum, but it allows some kind of repetition. So it basically involves an encoding process of a qubit into multiple qubits. So when there is an encoding, there will be a decoding. So the decoding process basically identifies and corrects the noise. So okay, here from the stabilizers we can see, okay, here is the noise, then we can apply that correction and get the corrected qubit. But what happens is when multiple physical qubits are encoded into a more reliable qubit, which is known as logical qubit. So this is a distance 5 surface code. There are 5 qubits in first row, 5 qubits in second row, and there are total 25 qubits. So basically 25 physical qubits are creating one more secure logical qubit. So this logical qubit is less error prone, but still some quantum errors can occur at all the physical qubits, but those are suppressed by the logical qubits. And the decoding process basically identifies the errors at the physical level. The problem is this mapping from syndrome to error. The syndrome is, suppose there are physical errors in this qubit, this qubit, this qubit. By X I mean bit flip error. Then the syndrome we get is this red dot. Why? Suppose in the previous slide we saw that for X errors, these corner purple stabilizers are get affected. So suppose there is an X bit flip here. So this stabilizer will get triggered. I mean stabilizers will give -1 eigenvalue if there is some error, and it gives +1 eigenvalue if there is no error. So if there is an error in a neighborhood, this will give -1. But there is another error. So these two will make this again +1. Similarly, these two errors will make this stabilizer +1, and finally this error will make this -1. So this minus in this entire structure we get -1 only here. So this is our syndrome for this error. But we can see easily that these 3 errors gives a particular syndrome, and these 2 errors give us the same syndrome. Now we don't know what error is falling. We only measured the syndromes, right? And by looking at the syndromes, our target is we will know the errors and put our correction. But when one syndrome can map to 2 different errors, then there is a problem, because this mapping is not one-to-one. This is the first problem. And the second problem is, suppose that the actual errors is in these 3 bits. Now we can see, okay, there is some violated stabilizers here, and our decoding, be it machine learning based decoder or be it any kind of decoder, our decoder can say that, okay, these violated stabilizers means there are errors in this and these positions. We don't know. We apply these 2 errors onto this structure, and as a result, we get a series of X errors in all the 5 qubits. So at beginning there are 3 qubits, but when we try to correct it, we get 5 qubit errors. And this kind of errors is called logical error. So there is many definitions of logical error, but a simple thing is, if in this kind of structure an error basically travels from this top boundary to bottom boundary, stretches from the top boundary to bottom boundary for bit flip, then it is a logical X error. And if there is some error that stretches from left to right, if there is any phase flip error stretches from left to right, that is a logical Z error. So let us talk about the traditional decoder, which is well known and used since a long time. That is the minimum with perfect matching decoder. It is based on the popular Blossom algorithm. So there is one way of, so Blossom algorithm, as you know, is a graph theoretic technique, right? So to use this minimum with perfect matching in a surface code, first we have to convert this structure, any surface code structure into a graph. So I am showing you one particular way of doing minimum with perfect matching in a surface code. So suppose this is our surface code structure, which we have shown previously, our distance C surface code. Now, for doing minimum with perfect matching, we have to first define the boundaries. So we have defined the boundaries writing B. So the blue colored B's are not here, right? So we have put them and we call them as dummy. And these boundaries are already existing. So these points, so these 4 points. So this is our entire boundary. So what we can do, we first, we can draw the nodes with the dummy nodes, which are basically the dummy boundaries. So we just map the blue colored B into these nodes. And then apart from these dummy nodes, there are some actual nodes, which is the violated stabilizer. So suppose there is some violated stabilizers in this position. This means there can be some error in 1 or 2, we don't know, but there is some error in this position. So this is the violated stabilizer. So we put this violated stabilizer as a node. Now we have to do the matching, right? And before matching, we have to define the edges. Currently we have defined the nodes, but now we have to define the edges. And for edges, the idea is we have to draw edges from this actual nodes to all the dummy nodes, but the criteria is we have to hop over a node. So from this -1, from this actual node, we can hop over this qubit number 1, qubit number 2, and we can hop over this qubit number 5 and 9. So we can't just match this qubit, this node to this node, because we can't match this to this, because we are not just hopping over any direct qubit. So this is one criteria. So this, for like this, we have created our edges, and then comes the matching part. And as I said, the minimum with perfect matching. So it will be a perfect matching in sense that we have to consider all the actual nodes, and the weight should be minimum. So we should not take this edge, because this edge weight is 2, as it hops over 2 qubits. But if we take this edge, this weight is 1, and we can take this as our matching. So what happens if we choose this matching? It says that, okay, I am choosing this edge, means the qubit it hopped over is erroneous. So from this syndrome, we can say qubit 1 is erroneous. We can check this by hand, that if there is some error in bit 1, this Z will get triggered. But there is some problem again, because I may choose this matching, but you may come and say, no, I will choose this matching. This is also correct. This is also a minimum or perfect matching. But then it will say it will hopping over this second qubit, and it will say bit 2 is erroneous. So there lies a confusion. In the minimum perfect matching algorithm, we can see some boundaries, right? In the graph theoretic structure, there is one original graph and there are some boundaries for the boundary conditions. So these are just boundaries. There is no qubit. These are some nodes only for the graph theoretic purpose, which are used to denote which qubits are affected. There is no qubit. The qubits are only on this 1, 2, 3, 4, 5, 6, and 7, 8, 9. These are the qubits. And in the minimum or perfect matching graph, we will not draw the qubits, but we will draw the stabilizers, the violated stabilizers as our actual node, which we have to match. And these qubits are like don't care conditions. So we can use these qubits to draw an edge. Suppose if there are two errors, suppose an error is in this position and another error in this position, then we will have two actual nodes, two red nodes. Then we don't have to use any dummy boundaries. We can just draw an edge among them. But as there is no other nodes, we have to use the boundaries. But these are not qubits. So there is another problem lies with minimum or perfect matching, that we have already seen this type of things in one of our previous slides, that minimum or perfect matching, from the name we can get the essence that it always tries to find the minimum number of errors that can recreate the obtained syndrome. So suppose it basically doesn't take into consideration the probability of error, but in reality all the machines have different probability of errors in quantum machines. So suppose this is a 5 qubit structure and these are all the 4 qubits creating this syndrome. But if we feed this into a minimum or perfect matching decoder, it always will predict the minimum error that can produce this syndrome, and the minimum error is this. So it will always say that there is an error in this position. It will never detect this long chain of errors. Now this long chain of errors is rare, but there is some chances that there can be a long chain of errors like this. And also the complexity of minimum or perfect matching is high. Now we come to the machine learning portion. So there are very many works in this field, because machine learning based decoders already showed that they are capable of outperforming the traditional MWPM decoders, and these papers already showed that in their results. Now, an important metric for this comparison, like which is better in terms of decoders, is the pseudo-threshold. Now, the pseudo-threshold is the probability of physical error below which any error correction can effectively suppress the logical error, because our main target is to suppress the logical error, because we are suppressing the physical errors by creating a logical error. Now, our main target is to suppress the logical error. And the machine learning based techniques are shown to obtain higher pseudo threshold than the minimum or perfect matching decoder, so they are said to perform better. Now there are two types of decoders. One is low level decoder and another is high level decoder. So in the low level decoder does what I have explained in my previous slides, that okay, there is some syndrome, so this should be the errors. And high level decoder basically classifies. There is no in logical error there can be 4 type of things, right? There can be no logical error, that is identity, or there can be X logical, Y logical, or Z logical. So high level decoder basically decodes what logical error is in it. It is basically creates any problem into a 4-class classification problem, the high level decoder. The mostly all the literatures I have read consider the low level decoders, or they use the machine learning only for high level decoders and other classical processes for the low level decoders. And one more thing is the existing literature focuses on the symmetric depolarizing noise model, that is there is equal probability of X, Y and Z errors. So our contribution, we have done a work that our contribution is we know in reality quantum noise is asymmetric. It is not symmetric or like this. So the phase errors are always more likely. So both symmetric and asymmetric depolarizing noise model for various levels of asymmetry is considered in case of distance 3, 5 and 7 surface points. And one more thing is feed-forward network and convolution neural network techniques for both low-level and high-level decoder for different distance surface code are used to show that the machine learning-based model outperforms the traditional MWPM in both the symmetric and asymmetric settings. And we have also studied the role of different complexity of feed-forward network and convolution neural network. Now I am briefing the machine learning ideas very quickly because there is a shortage of time, and these things are very basic. I think more or less all people know how the feed-forward neural network works. There are some input layers and one or more hidden layers and output layers, and each node is connected to another, and there are some weights and threshold, and these weights are basically gets adjusted while the training is being done. And this is the structure of the feed-forward neural network. And in the convolution neural network, what happens is it is basically used in case of images or patterns. Here we will deal with patterns, and there are mainly three types of layers: convolution layer, pooling layer, and fully connected layer. So basically the first few layers focuses on the simple features. It basically trains the network on simple features, and as the data progresses, it tries to recognize larger elements of the patterns. So the first layer is the convolution layer. Just to mention the basics, suppose this is our input image or input pattern, what we can say, input data. Then we have a filter, and it basically convolves over the input image. The filter convolves over the input image, and it basically multiplies, sums and multiplies all the position wise, and then we get our output array. So this is done by the convolution layer, and there are three main hyperparameters which affects the output: the number of filters, that is here we have using one filter, so one output array. If three filters, there will be three output arrays. And stride is the distance that kernel moves over the input. So this is the filter at first. So do we give a huge jump when we convolve, or we just give a uniform scan? That is the stride. And zero padding is used when the filter doesn't fit the input image. So we can pad some zero outside the boundary so that we can handle the size of our output array. The next layer is the pooling layer. This is basically downsampling or the dimensionally reduction. There are mainly two kinds of pooling. There are many kinds of pooling, but two popular kinds of pooling are max pooling and average pooling. Max pooling is basically, suppose this is our output array, and from this we get only the maximum number and take that in our next layer. So that is max pooling. It is only for the downsampling, while many information is lost, but the benefit is it will reduce the complexity in a much higher scale. And the last layer is the fully connected layer. It is basically like the feed-forward neural network, but a more dense version. So there are some activation functions used in CNN. I am not going into the details, but we have used value in the hidden layers, and in our output layer we have used the softmax activation function, because when we are dealing with multi-class classification, as we have said in our high-level decoder, also in our low-level decoder, all are basically multi-class classification problems. So we have used the softmax activation function there. And let us come to the noise model we have used for our work. We have already seen in the circuit of the surface code that the error correction cycle consists of 8 steps. So if P is the error probability in each step, then the total probability of error on each data qubit is 1 minus 1 minus p to the power 8. Now this is our noise, this is our physical error rate we are considering. And one thing to mention, that we are assuming completely noiseless measure qubit and a perfect measurement, which is basically an assumption and an ideal scenario. Now, how to do this simulation? I mean, we have a model of d cross d surface code, and now we have to turn this into a classification problem. Firstly, any ML decoder does a mapping of decoding to a classification problem, and for this consider our distance d surface code, and each of the d square qubits, so there are 9 qubits here, may have an error with probability p, right? So for bit flip or phase flip error model, there are 2 to the power d square possible error combinations. So this is basically a classification problem with 2 to the power d square classes. Hence, This is feed into the ML decoder. Now this, I am talking about the pure implementation purpose which we have done in our code. That is, this is the structure of surface code. There is some error. We don't know this because we can't measure this error, but we can measure the stabilizers. So suppose there is some error, then what will happen? These two neighboring stabilizers will get affected. So we denote these affected stabilizers by 1 and all the unaffected stabilizers by 0. Now these blue colored are dummy because we wanted a square structure to feed into our convolution neural network or feed forward network. So these all are 0 and only the violated stabilizers are 1. Now this is our input matrix which is basically trained, and this is our labeled data. This is a supervised learning, and thus we can train our ML model as we want to. Now one thing is, let's check the logical error problem once more, which is also possible in this kind of ML based techniques, not that it is only possible in minimum or perfect matching. So faulty errors can lead here and some errors may go undetected. Now why the logical error are such of interest? Because we can't see the logical error. Once there is some logical error, we can't detect it, because normal physical errors are detected by syndromes, right? So if there are some errors, we can see there is some violated stabilizers here. So suppose there are 2 bit flip errors here. These 2 bit flip will not trigger this -1 and -1 will make this +1, but this will trigger this portion. This will get -1. So we are writing -1 as 1 and +1 as 0 for our implementation purpose. So our syndrome is this. This is our syndrome array. And by looking at this, we can, the machine learning decoder or any other decoder can easily predict the actual error is this. This is a wrong prediction. So now if we apply this correction into this bit 4 and 7 and actual our prediction is bit 1, then we get an error in 147. So this is a logical error. Now why this logical error is scary? Because in this logical error, no stabilizers will get violated. We can see this from the picture. From these two, this will get stabilizers, and from these 2 errors, this will get stabilizers, and we will see no error, but there is one error. So this logical error is basically scary, and we want to decrease the number of logical errors. And we have already mentioned the pseudo-thresholds, and there is another metric called thresholds. Let us see all these 2 things from these 2 graphs. The pseudo-threshold is, this is our physical error probability. Suppose we are plotting our decoding efficiency. So this is our physical error probability. And for depolarizing noise model, the blue line, this is our logical error probability for particular physical error probability. So if you see the cyan line, it is basically where the physical is equal to logical. Means there is no correction due to this logical qubits. So our target is to keep below this line, because below this line the physical error probability is higher than the logical error probability. But once we cross this line, the logical error probability is higher than the physical error probability, and we don't want that. And these points of intersection of these decoder curves and the cyan line, these points are called the pseudo-threshold. And the threshold is one general concept is, if we invest more, we will get more security, right? So for d equal to 3, we get some sort of security, but if we get some d equal to 5, 4, it will be more secure. So that happens with when, suppose we can see here, for a particular physical error probability, the logical error probability is higher in D3, the blue line, than the orange line in D5. But there will be a point where these things flips. There is a particular physical error probability where these points will flip, and this point is called the threshold. So this pseudo-threshold and threshold are our metrics for evaluation, and had the values of those metrics, the better is the performance of the decoder. Now let us come to the comparative study between, we have trained our model that is feed-forward network and convolution neural network as decoders, and we have tested the performance with the MWPM based one. So here we can see the MWPM decoder This is physical error probability versus logical error probability, and these are all for the machine learning based decoders. And uh, the first row is for the entire physical error probability with which we tested, and the second row is basically a zoomed in version of these parts, so that we can actually see where the lines cuts the cyan line and what is the actual pseudo thresholds. And this is only for d equal to 3. For this is only the pseudo thresholds we can see from here. And to check for the thresholds, we have to compare between d equal to 3, 5, and 7. The structure is same. This is for the MWPM, and this is for the machine learning based decoders. And let us see the chart from where we can just see the numbers. So for minimum and perfect matching decoder, for a symmetric depolarizing noise model, for d equal to 3, the pseudo threshold is 0.0011, and our feed forward decoder for the same setting gave us 0.012, and the CNN gives almost the same. So these pattern basically replicated in all the results. So both for symmetric and asymmetric, we get these terms of these times of betterment. And one more thing we have noticed, that increasing the complexity of machine learning models. So suppose we are using higher number of nodes, higher number of layers. This basically doesn't providing higher decoder accuracy, but the training time is increases significantly. So here we can see different kind of simple or complex machine learning models, but the accuracy is more or less overlapping. But here we can see that the parameters is increasing so much for the complex machine learning models, and hence the prediction time and training time is also very much increased. So to finish, we can say that these machine learning decoders basically shows an increase of pseudo threshold by approximately 10 times as compared to minimum with perfect matching decoders. But again, there is this assumption that we have considered an ideal scenario where there is no measurement error, no stabilizer error, and we have also shown that simple machine learning models are sufficient to provide optimal or near optimal decoding performance. And the training, basically the problems of machine learning lies in the training time and number of training samples, because it becomes a bottleneck when it is of larger d, because we have seen it is a 2 to the power d square number of classes. So when d is larger, this becomes a very much tiring to train with this large amount of training time.